Okay. So now you guys can hear me. Alright, so my search box doesn't get in your way. Alright, so we can see I got a bunch of stuff in front of me. So we're gonna go up. And we're just gonna look at what we got. We have SuPosXt. Yep, SuPosXt. Superposition text. So we are superpositioning the text to a font called Node, which is just a physically encoded font. It's just a font that physically encodes itself, so you just can't see what you're typing. Let me show you what we're talking about. Or suppose it. Alright, so we can see we are typing, and if I was to inspect right here for like what we're typing, I'm just going to type in the letter G, lowercase. I'm going to type in the lowercase t. I'm going to type in the word hello with capital H. So you can see no matter what I type, it does not show what I'm typing. Now if I want to see what I'm typing, I just go like this, and I can see hello world right there. And we can look in the small text over there by that ad, and my sponsor reel, you can see right over there. It says hello world inside of there. So refreshing this, hello world, and this is what it looks like now. So we can type in about 45 characters before we start producing a block or a graph. So I'm going to go ahead and finalize the next one. So we're going to have a graph and a subgraph. So here's a graph. Boom. There it is. Graph. There's the text that I put. Well, actually, none of that is what I typed in. Even the binary code you're seeing in there is only the state changes of what I put in. And then we're only recording the actual font position of those nodes on the font. The font's called Node because it's got these little nodes. These little boxes. Some are open, some are closed. Some are talking, some are not. And that's the entire language. So we're just recording how those appear in a graph. And then we are recording those state changes on the graph in the same manner, and then putting those into a Hamming code graph. So this is compounding, so we're actually compounding different kinds of graphing. So we're using graphed entanglement for graphed data into a entangled graph. So compounding Hamming code, and they're all extended Hamming codes. So compounding extended Hamming code. You know you love to see it. Alright, so we type in, so this is a subgraph. A subgraph does not have, does not point directly to, like, well, technically it's pointing to another hash. Like, if I take the previous, and we decode that, we would get 1245 45, and if we look, it directs to 1245 45. So we can see that right now they're stuck to a 45 limiter. That's going to be the max cap, where you're going to have flexible setups, and I do want it to work within a 255-bit grid, meaning what it will do is it will subgraph in every fourth subgraph every time you get to a point where you are going to be like, alright, this will fit within 255 data block. It will graph all that together into a single graph, and then basically we're trying to figure out how to take these graphs and basically the same basic concept but with these graphs. So until that happens, you just produce subgraphs, and we're just going to make them to where they're more flexible. So when you end it, it just ends. Like right now, when we have to, even when I click one button, I have to finalize the graph. I have to tell it, hey, I'm done, you know. But right now, when I do that, what it actually does is it just fills in a bunch of extra data. So as you can see, some of these, like 1045, that means they're the same height and length and width on the inside. It means nothing's different. Now see, this one is 1245. This one's actually a different size. This one has technically more data than the other two, because it's got 12 loop sets for 45 bits of data, or 25 characters in this case. And so those will be more dynamic. And that last number is the weight number of this chain, because it's technically what it is. It's a chain. So that will eventually, because the blocks will be the graphs will be more fluid. You'll be able to make smaller ones and larger ones. So those will change also. So you can have really unique characterization or even number sets. The great thing is a lot of that can be adjusted and changed, and we do want to get to a lattice version of this because it's should be perfectly capable of handling lattice style encryption. Now let me get you back over to what I'm now looking at. Well, see, the part that isn't working right now is the decoder. So the decoder is supposed to allow me to be able to take this. And I had some versions working. I'm going to show you in the code. So I have a version that kind of works. So I'm going to try it again. We're going to try to adjust it again and try to basically be like, I just want to do better, man. Got to make it better. So we can see here the node font. We're bringing it in from IPFS. It's an IPFS font, so anyone can have access to it. So there you go. There it is. If you want access to it, the CID or the benzine is what's being used here. One of those BASC hashes, Bayesian hash right there. So we're just basically, you can see that the actual what we have here is just pretty simple. I have body of what we looked at. It puts a text area there, and we have two text areas, encode and decode. Pretty simple, bro. When you put stuff in, it reads it. The only one that allows to paste is decoder. Encoder does not do that. And decoding at the moment, you cannot type. So eventually we'll get that buffer system put in. In case you're wondering, that's how you type on a decoder and how you can paste in an encoder. I used to use a paste encoding buffer thing where it was like, it's just an automated service. So I don't want to use that because I want this to do it all locally. I don't want to have to rely on anything like that. Once we're pulling from IPFS, we should be done. We want this to be able to run with IPFS. This shouldn't have to be anything more than what it really is. Yeah, there is a special things in there. We do have some node practice being done in the site things. So, alright, to the gist of it. So basically we have a couple of situations where if it comes to where the data is about to be leaked, so we're about to show what we have inside, we erase everything. So even if you just change the font, you go, hey, look, I want to pull in another font. When it pulls in that other font, it should erase it. What this does, this creates a bug. And we have somewhere else that says if there's nothing inside the text area, it needs to be cleared anyways. Like all the data points, the inner value, if the value is gone, the inner HTML needs to be output, needs to be removed, or inner text needs to be removed. The output needs to be removed, like little things like that. So I think only one that doesn't do that is the encoder. Doesn't remove the output. The decoder should remove the output. And doing these in combination to each other allows us to have that feature where I can just select all, delete, and then I can actually see what I should be seeing. So, like if I don't want to use it for the graphing, I just want to use it because it's a cool looking, fun way to type or something. It definitely showcases that. And if you have, if you're putting this into it, that's the whole point of this. This system needs to have this extra little bit of availability for the users, people, the everything. I'm just now realizing you guys are never gonna be able to see this. Is this transformed? Probably. No. What? Not transformed. There we go. That's really confusing. And now you guys can read again. Alright. So now we're going into the actual transmutations of the stuff. So you're going to hear me saying things like transmute, encode. We're not actually encrypting anything. It's very important. We don't want to encrypt anything. So when you encrypt something, that is going to be looked at from this, like, it's already is, like, countries are already looking at, like, hey, bro, that's a problem. We can't have you encrypting things. We want access. So one of the tricks we have up our sleeves, though, things that we can use, is we can entangle. We can encode something and then entangle that encodement. Don't know what the fuck is there, but if you have the right skills, you can detangle it, you can decode it, you can find out what's there. But that also means that I could send you something and not have to tell you how to decode it. You just have to have the right skills or the right tools. And that's really the key here. We're making a tool that people are going to be able to use as an encoder and a decoder. This is going to be the thing that you're going to be able to get on your cell phone, your home. Actually, I was using it on a cell phone the other day. Encoder works just fine on a cell phone. But one of the things that one of the reasons why this is important is private paper. So before we get into the transmutations and how the encoding is working, let us show you the best example I have to show why transmuting is actually really useful. Why encoding works. See, now I know why that thing was. It's because this other screen is a completely different size. That's fine. So now you shouldn't be able to hear what I'm listening to, but you might get bits of it here and there, so please don't hate me if you get little bits. That's just being picked up on my mic. I have the audio set real low, but I think it's still being picked up. So anyways, this is why it's important. This is a way to have freedom. This is digital freedoms that you can download and use. It's private. So we have a version of this that outputs a private version, so it's like really, really freaking private. I want to make it more private. I want to make it a JavaScript secure enclave. So the text area, the thing that you're looking at right above me, this body of area, this thing right above me, text area, I want to make a secure text area enclave that can be appended into HTML. It's only through JavaScript and not through any other meaning that if you was to put this in the darknet or something like that, a large portion of your traffic users won't ever see it. It'd be gone. It'd just be invisible. So is this entire site. Oh, well, one of my cameras just died. Oopsies. See when we get that back up on online. So that's why my arm stopped working. But anyways, so we want to secure these a little bit more. We want to make them work better. The one that we have that is designed around being private, more private than this one, we want that to be real. We want there to be a button where you could like secure, and you could secure it, or you could secure everything you're typing from the second you pull it up. You just have to know what you're typing. And that gets to a point where if you have someone who's actually fast enough in typing, you know, they can really go. I suck at it. I'm slow as heck. I really cannot go. But when you have someone who can type, like insane, it would, and this is the type of stuff that I'm typing when I'm just messing with the suppos. You can see I'm just typing literally as fast as I freaking can. So, and this is handling it like a champ. Bro, I'm streaming. I got the VTuber. I got music playing. I just activated things. I even overflowed JavaScript. But it still works. So this is block directed data. But alright, let's get to the actual. This is why you guys are here, right? Let's get to it. Now you know what's going on. Now you get to understanding the point. Let's get into it. Oh wait, hold on, I gotta adjust this. You guys go. Alright. So the actual full house whatever function. So we get what Gibbler tells us what's going on. Gibbler says, bro, here's what you just said. Gibbler looks for the actual input. And the second Gibbler sees an input, well, it's pretty easy to tell there. We start tracking how many times Gibbler says something. So, just, there's many episodes where there is someone that tells you how many times, or how many words Gibbler says. So, we do the same. So Stephanie basically tracks what DJ says. Okay, so Stephanie doesn't even pay attention to what Gibbler is saying. DJ just repeats what Gibbler says in Node. And so Stephanie just keeps track of that. She keeps track of the state change, the shape, right? Shape? Yeah. The state change of the shapes. So she just says, hey, if I see the node is active, it's like a 1 or 0 if it's not active. So I just record that on 3 rows match. She has activists, and she's moving them over based on if she sees, you know, a node is active or not, and has 2 different sets of colors. So one color is one set, so we got 0s and 1s. We got binary system. Oh wow. And then yeah, what DJ says, which is just a restatement, which is just exactly the same thing as what Stephanie's doing, restating. So we got a letter counter that tells us the length of what Gibbler said. We have came in here twice. Yeah, okay, came in here twice. Weird. That's probably not supposed to be there, but I'm just gonna leave it because I'm gonna fuck with it. It works. Okay, so we see we have delta, we have alpha, we have some variables, just basic stuff. All right, cool. And we can see we just taking in input. And basically, if there's nothing there, then just make sure C equals C, which should be 0 all the time. And we're going to eventually have a function here that looks for if C is not 0. That would be an error. So C becomes error correcting. For example, if it came out to a different number, we could just adjust it or something, or we could find out why, and then adjust it. So now here again, we are ensuring that things are, the buttons there, so you can when it's needed. So just some visual functionations that allow the user to have actual functions. Here we're actually mapping out the graph that Stephanie's using. So there is a very basic, like 4 wide, 3 high graph with but it rotates on a center axis, and that center axis is the N, or full stop, or the null position. Is what I've been calling it, null position. So the null position is like where, you know, certain things that are in the center go. Because if you look at the node from earlier, in the top font, you'll see that a lot of these are all focused around a center point. And that's how the font is used to ensure that it knows that what font is what font. Like when you, to ensure that it's visually and mechanically decodable. So it's not just jumble, it's real. So then we're like, okay, here's an example of what we're looking at. This is our extended Hamming code grid for compounding the Hamming code, for compounding this graphs. Here was some just me trying to, like, when I come back in and you're like, okay, how does the Futurama Theorem really do this stuff? It just kind of explains it. We even have an error flip bit where we can flip bits if we think there's an error, so we can force adjust and little things. What happens if these things are done? What if Gibbler's not saying anything? What if blah blah blah? What if, you know, basic things, first things I always want to cover are things that problematic, right? Might cause issues, might cause errors, might cause problems, blah blah blah. Good song. So that's fine. So we say, hey, DJ needs to transmute what Kimmy says for her parents. Actually, I think that was wrong. It's supposed to be Ghibli. And Steph needs to track what... Kimmy Gibbler, yeah. And Steph needs to track what progress is being done. And then Michelle tracks the shape order. So Michelle just sees the shapes. And she writes a number to represent that shape. While one person is actually keeping track of where on a grid they appear. So imagine, like, they're building stuff with Legos. This is how I thought of it in my head. There's a thing that's just spinning, like, and they're building onto that, like it's a Lazy Susan or something. And anything that would be like the null, they just throw underneath the table, okay? And so that's where null is, just under the bottom. Kind of just forget about it for right now. And then they're building everything up on the top, based off of what's going on, and that's the shapes. And so for every layer of new shape, Michelle just writes a number. You know, she don't really know what's going on. So here we now have what everything equals. This is for, I think, the standard Latin alphabet. So it could definitely be expanded. I mean, the great thing is, like, the encoding part doesn't really matter. Like, all this stuff right here, as long as, like, this bit can be transferable to someone, like, as long as you, this is like shared knowledge information, right? If you don't want to create your own, you don't have to, but the point is like, there's more room for creating more versions of these. They don't have to be reliant on this one. But the actual math and stuff, the way the encoding actually works is the same, and the way the decoding works is the same. So generic processes of encoding and decoding that, you know, eventually will be like, hey, yeah, what's your call ID for your it would be like the girl's variables. What's your girl variables, bro? What are the ladies saying, bro? Like, these stuff right here, these are the girl variables. These are the variables of each character that could be pressed or used. So then when we get down to the bottom, we take the Z, which is the length of Steph. And for some reason, Stephanie's length, we need to find her longest length. And we only care about the longest one. So then we have an alpha state, which, if you don't know, that actually is the Futurama code. That's the Futurama Theorem's math formula. And that actually corrects and ensures that our Z state always realigns to the center. It's freaking awesome. It's the only reason why Futurama Theorem is here, and then I was like, wait a minute, if that works for that, and then someone was like, well, you know, if it works for that, then it works for this, and I was like, well, if it works for that, then it works for that, and then it's used throughout this whole thing. Is we just use Futurama Theorem to basically self-correct everything we do as we do it. So we let some people from the future fix this. We fucked up, okay, in the future, and it somehow fixes us in the past. All right, it's like someone in the Futurama is watching Full House and they accidentally kick something, and then you see it get fixed in the show, and they're like, "Bro, do it again." So when they see something messed up in the show, they just do something. Boom, fixes it. Okay. So here are my shell values. These I have. Oh my gosh, I have them all over here because like I keep forgetting what they are, and they are not easy. And it's designed. It's supposed to be easy. It's supposed to be simple, basic thing. Yeah. All right. Okay. Here's the 17 grid. It's kind of what it looks like. Just visual representations. This was really difficult to visualize to try to start coding. So I got a lot of stuff to help me remember what am I doing, how does this work, what about this, what about that, and some of this we don't have fully set up. We don't have the trinary or the API stuff set in yet. Right now we're just doing detector setup, which we're doing stuff like if we're using trinary or API markers, you want the length when applied to the Futurama theorem to equal either a 0 or 1. And it's like, because like we have a modified Futurama theorem that no matter what we give it, it gives us either 1 or 0. Okay? So we can put stuff in these spots for detectors, these determiners. And if in the Futurama theorem it comes up to a 1 or 0, that is what we are considering for the determinators. So even if it's not just simply a 1 or 0, we can determine if it's 1 or 0. It's freaking amazing. And it will allow us to do so much more. Because in the future, we're going to be able to do stuff like we're going to be able to encode completely unrelated data to unrelated data. And using these setups where using this modified Futurama theorem, if it outputs to 0 or 1, you know. And we're gonna basically, like, okay, so right now to error correct, you need like for, I don't know, it's like 0.9% of whatever, but now we're talking like, oh no, we can drop it down even more, where we don't even need anything to actually be like this is a detector zone. We just go, if you check between this point and this point and it's a 1, you're good. But if it's a 0, now we need to check the next sets and the next. And yeah. So we can have these like really strange where it's like I only need to detect based on if I got a bad output. So I only need to look further down the line. And I wish I don't have the things. I have pictures somewhere. Hold on a minute. Let me go to the pictures. I'll show you guys what I'm talking about because there's pictures that will show what I'm talking about. So I'm just waiting on a call, and I thought I'm just gonna do this. I've been seeing a lot of more people do this, and I've just been trying to get notice for it. So here. So if we pull this up, alright, so you can see there, the detector is saying 222110. It was messing up at the time. But we can see that it noticed it messed up. It puts a 2 after the other 2's, and it says, hey, I believe this is what's supposed to be here. And then we can see 1100. So what was that supposed to actually be? It was supposed to be like 111 0010, then 1101. That's what it's supposed to be. So I was complaining because it wasn't working quite right. And we can see that if we look down, obviously it wasn't working quite right. Something was wrong. And the modified Futurama theorem fixes what was wrong. But that's what I'm talking about is, okay, we have spots here. We can obviously see where we are pulling these numbers from. 1, 1, 12, 45, 0, and if you go down, 1. So, what if mtj4ndu equals, that outputs 1. And then 12 by 45 outputs the 1. And then that first set of row string outputs to 0. And then second output string outputs to 0. And then, then we can have at the very end, because we actually have a spot for this. Like if you look, there's actually a spot in here where there's like a period. There's a comma period. There's supposed to be something in between that period and that comma. And then if you look at the very end, there's a comma at the very end. There's allowance for more data at the very end. There's allowance for, I think it was 8 more points of data. But they all had to be simply a 0 or 1. But we can basically put the entire determiner at the very end, and it would be able to determine all 8 sections of this compounding Hamming code graph. Alright. Look. Blah 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 blah. Blah 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 blah. Blah. What? Hey. Hey. There we go. This button, this button, this button, reset that one, close that down. So, that's the future, that's thing. So we're just going to keep going. Alright, so now we build a subgraph, fun stuff, basic stuff, just searching, subtracting, because of, if you see, do that, do this, this means. Then we're creating subgraphs, or we block the subgraph, which is that stuff cobalt right there. You can really see I use really good positive terms here. If it's strong and hard, it's a metal. That's metal. Yeah, so then we just kind of some gibberish there. Just explaining, because we have basically 2 sets of things. Basically, we run off a Turing machine and a counting machine at the same time. And so we have 2 different reference points for everything. So everything has 2 different versions of itself. One's a counter machine version, and one's a Turing machine version. So then as I'm going through these steps, we have to flip-flop back and forth, so I have to know which one's which. And we call one offset and one regular set. So you can see I have a see me, set me, in-step programming key, so we can change what we are looking at, what we need to be doing next on the fly, based on what we do now. So what I do now can change what I do next. So this allows us to have really dynamic programming, which can handle shit. That's the ideal here, is that it can just pretty much handle whatever we throw at it, and it will take care of the rest. We use guidelines, current markers, all sorts of little things. Knowing when to clear a state, when to store a state, when to all sorts of things. Then we're looking through, okay, here's loop cycle information, here's more just literally notes of don't forget, don't forget, don't forget. And the hardcore stuff, what's longest, and determining all this stuff, putting them in the right locations, in the right order. Going through, making sure all of our loop sets are ready. We do our adjusters. We start doing our determiner checks. And we start going through all these different steps. Now, the determiner checks we want to do in the future, they're going to be simplified, more simplified, like where it says here, if blah, blah, blah equals blah, blah, blah. There's going to be a step before that that just says, hey, this, blah, blah, blah is this through this. And it's going to make it easier because we're going to basically be able to turn everything down into a simple state. And then we're just going to have to ask, hey, is this a 0 or is this a 1? And that's it. And that's it. And then if not, the list the last thing. And so that's what we do here is we do a if else. So you can see we have an else statement with 2 if else, and we're just basically saying, hey, what's the most ridiculous thing possible? What's everything else gonna be? Oh no, what's the most common thing possible? What's the next most common thing? What's the more ridiculous thing? And then what's the least ridiculous thing and the more ridiculous thing. So we handle these tiny little things in that order of more common, least common, more least ridiculous, more ridiculous. Okay. Now we are only going to pull from recorded state changes, not the actual row arrays. This is really funny because the detectors we laid down are based on after state changes. The determiners that we read after the fact are only of the data. It's freaking insane. But that's the point. So areas where the data is live or raw, or has been live or raw, we don't want to mess with it. The second we turn it to something else, we never want to think about it again until it hits decoder. Then let the decoder handle that. And that's kind of the ideal here, is this back end, front end is all mixed together, allows us to do things like very quickly get rid of what was said or pressed, and then work with that data, knowing that I know what it is, but no one else knows what it is. Even if you check the code, there's a chance, even just looking at this, you ain't going to tell me what's going on. You might have to sit here a while, and by the time you get done, you might be able to call yourself part of an expert or something. And I say that just meaning because, like, it's like, yeah, sure, Hem encode is basic data output. We're not using it directly to the strict manner of what most people would, and we're adjusting quite a bit. So now we're actually doing the actual Hamming check, which is just compare if the number of ones we have is even or odd. Simple as that. And give us a 1 or a 0 based on that. So we finish the graph, and this literally just puts the data into what you would call a block and outputs it. Boom. Done. Roasted. We reset our visuals, reset our information. We have debug points for these endpoint things. It got complicated here, so I needed to put more in as we were doing stuff. We can see there is a point right here for dynamic latticing. There was actually a spot somewhere earlier, we probably just skipped it real fast, where we can adjust an entire set of maths. So if we do have latticing, this is where we'd have to reset it. And then blah blah blah, actual output. You can see here we're starting to see a little bit of Futurama's code coming back into play. The actual end output. Right now this is the early run output, so when you click finalize graph, what you're actually doing is we're changing the number of, like, because it won't let me change the number that is used that checks if we're done or not. So I just have it say the same thing a bunch of times. One part of it is random, as you see down here at the very bottom. We do have a random point of entry because the system is designed to look for repetitive data, so it messes up for some reason when it sees it. Probably because it thinks it's being manipulated. So we have to put in some point of randomness into our sponge value. And I basically want to figure out how to take this and make something for real out of it. So that way when we do what we were doing, we'll be able to just, we won't have to like run through the whole Futurama code, full house code. We'll just be able to say, hey, look, here it is, da 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 da. We'll figure that out. See, the part we're actually at, though, is the decoder. So, decoder is below. This is where we're at. So this is where it gets tricky. So we're going to clean house. Okay? Whenever the girls clean house, they talk to Becky. Becky then figures out what's going on, and she's able to fix things. So we're going to clean house. We're going to get Becky online, and we're going to have Becky translate the information back for us. Okay. Ugh, when does Becky move in? I don't know, but damn it, girl. Let's figure this out. So, we can see we need a lot more variables, and some of these, I don't even know if I'm using all of these anymore. Some of these are, I had one ideal, it didn't work. I have another ideal, it didn't work. I have another ideal, it didn't work. I have another ideal, it didn't work. So instead of getting rid of all the values, some of them I reuse, and now I'm at a point where I don't know which ones I actually need because I don't have any stable working version. We actually decode everything back to Stephanie. And now we're at the point where we need to have Michelle, we need to look through Michelle's gibberish and find each shape. One at a time. First I tried just, I know what all the shapes look like. Just capture them. Okay? So, let me show you what I mean. Yeah, so we have this fun little thing here that collects between 3 and 4 digits, you know. No matter what's in the string. We can at least 3 digits up to 5. So all these little things, and so we got this. It looks for HE followed by L of at least 2 or more, followed by O's of at least 1 or more, and capture all of the manners within here, and capture all the ones in the manner within here. So capture the HE plus all the L's plus all the O's that follow, as long as they match HELLO methodology or more. I could limit it down to strictly just 2 L's. And or also capture any capital W that is followed by any digit that is also immediately following any amount of word and of at least 1 word or more globally on the scale. Not only does it match it, it finds it, and we put it in order of where it's at locally on the system. Now, unfortunately, it does not differ between the hello and hello, because hello is also in hello. It just sees those the same. And I was like, okay, that's something I can figure out. You know, that is something I could figure out. If I have 2 that point out the same, I take the first one and I just cut out that value, and then I search again. Is this still here? Yes or no? And if it is, regard or not, it don't matter. I'm going to do the same thing to the next one. And then I just figure out which one of the 2 isn't there. If they're both there, we cut out those, and we do it again. Well, we only cut it out if they're the same. If they're not the same, then we determine that there are multiples of these. We have basically whichever one is whichever one is shortest is an extra. So we'd say we have 1 extra of the shortest one. Because, like, again, hello can fit inside the other one. So, yeah, that probably would have been the first thing we would have needed, though. Hey, can I fit this inside that one? Because if so, I can just remove the longest one and then search again for the shortest one, and it should pop up. And then if we search for the longest one after that, it shouldn't. Boom. We're good to go. So I was like, okay, there's a way to determine that, there's a way to do that. Cool. So going to go back to the code, show you the code where it doesn't work. So, oh, that doesn't do anything. So if I go down, as we can see, we're just bringing in information, breaking stuff down to where it's at. Simple. You know, I think loop handling. Okay, so here we're mining out the rows. So we're actually taking the state change, and we are we are resetting the faux qubits to the state it was at. It's really confusing. It's the best way to explain what we're doing here. We're just taking what we have and using it to reset the area we're going to put everything in. It would be very similar if we had a quantum machine. This would be resetting the qubits, which would be aligning the machine to the qubits by adjusting it per radio wave for magnet signal, that one at a time, boom, 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 per whatever, one at a time, based off of the read tape. So you read one read tape, you record to the other read tape, per action you check, is the read tape empty in this spot, yes or no? If that spot is empty, based on the other information of what you had from the read, you do action whatever it tells you. If it's not empty, and it does not want it to be empty, you move on. If it does want it to be empty, you then perform, you let it know and perform. Or you move on into the next one and you perform. So, like this basically says, after you've read and you did something because you read, it will then tell it either it wants to move forward or it wants to check. And if you look, it's all happening at the same time. For all of them. All rows simultaneously are being checked in this manner from the same to the same write tape. It's insane. So, reading 3 tapes at once, writing to one singular spot. Here we're actually ensuring that we are only getting binary code. I just realized you guys, I forget, my bad. So we are like literally just using the Futurama code to, basically I don't care what's there, okay? If before it's a 0, we do one specific equation. If before it's a 1, we do a different specific equation. If it's neither, we do something else. And if it's neither of whatever those bounds are, which mean basically just says, hey, is there any other one of these longer than this one? Because if so, I don't want to do anything. But if not, I want to say we should be done. I want to put my hat in the vote and say we're done if no one else is longer than me, because I'm done. And then we do that for all of them. Here we go. Now we've decoded what we have. We can end the mining. Now we're in the determiner section. Here now we start reading the determiners. When we read before this, we only get errors. We read after this, it works. Of course. We only determined if there was, we only recorded our determiners after encoding to then check it after decoding. I still don't get why it worked this way. It just does. So we do it this way. But it's kind of cool because if you actually, one of the things that taught us this way worked was I kept getting errors and ended up being in the mining. And when I fixed that, the error went away in the determiner. And I was like, whoa. Whoa. the determiner is working in a manner it shouldn't be. That was confusing because I just moved it down here to get out of my way so I could have closer access to some of the data we're looking at. And yeah, so then it just like was working and stuff, and I was like, huh, da 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 da, you know. So yeah, lots of fun trying to figure this stuff out, but it does what it does. Now, I'm still trying to get down here. I don't have the fast thing. Yeah, tons of consideration there. So, right now, this is the current decoder. It does nothing. Information. Okay, so, as you can see, there's actually stuff here. We have all of the known shapes in this set. So this is something that could be pulled in. Something that we could easily say, hey, what's your CID for your known shapes? For your what your girls say, the scripts, whatever. I don't know what the fuck to call them. We could ask for this. This could be given to us. We don't have to know this beforehand, but knowing that there is a standard means that this works just fine. So we say guide is locked at 0, it never moves anymore. See, all the other ones, what we were doing was we were just like moving the guide number up as we checked stuff. So we would see how many positions from the read head do we have to check to determine things. And then we would adjust the guideline for the next rotation for that. So each time we would go through these loop cycles, it would be looking at something new. Now, this time around, we want to kind of do the opposite. We want to go, I don't really want to move the read head, you know. And as I'm writing this, I'm getting to a point where I'm going to end up moving the read head probably. But the initial ideal is that we're just going to splice or cut out what we take and then read from the beginning again, start over. And it should work. Because right now I have a method that will show me, it will break everything down to individual spots. It'll just basically read every spot one at a time and then tell me its probability of where it should be stored at. You know, which in this case it just put everything into null, just throwing everything under the table. For obvious reasons. So here's still what we have left to do. We only have one more step to do to actually have a properly encoding and decoding working system. And then everything else is to make it better. Yep. So here's the very first way of I'm just going to try to capture everything and then do micro loops to put that into the locations of that in a string, so we can then just grab that. That was the idea. We would just then grab it after that, right? I just grabbed that exact thing from that exact spot. Yeah. And the problem here is a lot of it comes down to I have a 0, but there's a possibility of a 0 being in everything. So one of the first things you normally would want to check for is the smallest 0. And I can't check for 0. That has to be the very last thing I check for. I'm screwed. So this is the second way. This is the one where it says here it only reads from the very last statement. So it only reads per slot at the red head on the read tape. That's it. It just reads whatever that one sees, and that's it. And it's a little more here, and we were trying to break it down a little bit more thoughtful. Okay, we have doubles, triples, like different things like that, where they all require 1 through 4. So let's look for those. If it's 1 through 4, pull it out of the pile, and let's then take a peek. And we just kind of look, see how many times it's 1 through 4 in a row. If it's triple, okay, triples. If not, then it's a double, and so we have all these different things. And then we get down to a point, it's none of that. Oh, well, is it at 3, 5, 7? 3, 5, 6, 7, or 9. If it's one of these, and we do these other things that are more complicated objects. So basically, we're breaking it down by complication. We're finding the simplest objects, we're finding the more complicated objects, and then the more complicated, I think we're going down here, there's more complicated objects that we're looking for inside that list of complicated objects. And then we get down to a point of the unusuals, the things that these other ones would just bug out on. It's this. And I had this at the beginning, and it would not work at all. And then I put it down here, and it started working again. So it was important that this has to be at the bottom, which is the thing that allows it to just singly read one at a time, which it would then pull T. This one right here, I'd go all the way down to the last statement of else, and say. And I also had this at the beginning, so it also didn't work. But you put it back down here, and it worked again. And that's why we have this if statement right in front of it, because it was an else if statement. It was, this was an if statement, and this was an else if statement. And I tried them all as if statements. I've tried them in various different combinations, and it don't do anything. Now, I was hoping to be here longer than this, but unfortunately, I have to run away.